name is Jörg Henris. I work for the Australian Bureau of Meteorology, so you're getting a real long distance presentation here today. I'm presenting about PSyclone's PSyData API, or the way I see it is tools, tools, tools. I had to split my presentation in roughly two parts. First of all, I go into a lot more details about how PSyclone transformations work, what they are, how you can write them. This will be repeated over and over again in the next day and a half, because PSyclone transformations are the very essential part of PSyclone. And then the second part is what is the actual PSyData interface, how to use this interface, and which tools are currently available and which ones are planned. This will be followed by a hands-on session, approximately 45 minutes, where you can hopefully see some of the tools actually in action. So first of all, PSyclone transformations. It was introduced before, just let me recap it a bit. So transformations allow to modify the PSyR transformation. Okay. I can't see my own slides. Okay, they modify existing code, and it also allows you to add new code. Now, the transformations are crucial for the separation of concerns. I'm a computational scientist, even though I worked for the Bureau of Meteorology for quite a few years. I'm not a meteorologist or any domain expert. Still, transformations is what allows me to optimize a code, while the domain scientists, the subject matter experts, work on the science. With transformation, the transformations can be independent of the code. They can also be specific. Sometimes I know for this particular code I need to do a certain sequence of transformations, and I have a kind of recipe for that especially example. But sometimes and quite often it can be very generic. Now, what can I change it for? I can change the code to optimize code, for parallelization, or for adding debugging features. Now, transformations are actually just Python scripts. You're using PSyclone objects, but it's normal Python scripts that you will be using to modify the PSyR. Now, I need to make a bit of a distinction. I will be talking about transformation and transformation scripts. Now, transformation is an instance of a class that modifies the PSyR tree and has two main methods. First of all is a validate method. That method basically verifies that it's legal to apply the transformation. If for whatever reason you can't apply it, for example, as a data dependency or something else, you will raise an exception. The second method is the apply method. Now, this will actually apply the transforms. Apply will always call validate first. The validate method is exposed to you because sometimes it can be useful to try various application of a transformation in your script and get basically feedback if it's allowed to do it this way or not. Now, in order to use a transformation, you need to create an instance of this transformation. Opposite to this is a transformation script. Now, a transformation script has a single function called trans, and it modifies the PSyR tree. This transformation script is specified on a command line for PSyclone using the -s option, and PSyclone is responsible then to call the trans function. Typically, the transformation script will then use one or more transformations internally. Now, how do you apply a transformation script? So on the command line, you basically add the -s option and then a path to the script. So in this example, -s/myscript.py, and the other parameters, name of the Psi file, name of the algorithm file, and the input file. As I said, this script must contain a trans function because this is the function that's being called, and it's called once per file. At this stage, any distributed memory modifications has been done. Now, I'm a bit ahead of my time. Rupa is going to explain this later in the afternoon. Unfortunately, it's a bit too late for me then to be around. But OpenMP, on the other hand, is added in at this step as a transformation script. So what does a transformation script look like? I will refine this as I go along. So transformation script, you define a function, trans, and it actually gets one parameter. I could just call it Psi. And Psi is basically the parallel system layer, which has all the information about the invokes and occurrence that you want to work on. And it returns the modified Psi object to PSyclone, which keeps on going to create the actual code. So the parameter is this top-level Psy object, and it gives you access to the PsyIR. Now, how does this work? So the Psy object contains actually a list of invokes. You have seen you can have several invokes in one subroutine, and each invoke can have several kernels. So each invoke is basically a nested loop structure, depends on the API. If you have seen in LFRIC, it's actually a single loop. In other APIs, might be 2 or 3 nested loops. It has a kernel computation. And if I say kernel computation, it can have various complexities. As you have seen in LFRIC, a kernel is actually a loop over a column. So it's actually a reasonably expensive function by itself. In other APIs, a kernel is actually just a single element of an array. So it's a very short and small functions. So we need to take care of this in some cases, as you will see later. So how do you get the invokes? There are 2 or 3 ways to get this. The best way, in my opinion, is you use the name. If you ask for psy.invokes, it gives you all the invokes, and it has a method called get, and you can specify the name. Now, name is actually what you have specified in the invocation. Eva will have shown it yesterday. PSyclone adds this invoke underscore in front of it. So this will actually gives you the invoke object for that specific invoke. You can also use an index number by using psy.invokes.invoke lists and then parameter n. It depends a bit how you structure your application, if you prefer the names or not. The most general way is probably if you want to loop over names. So there is a method called psy.invokes.names, which gives you all the names of the invokes. And then in that loops, you can actually get the invoke by calling PSyInvokes.get, which is exactly that function up here. Now, what you get from an invoke is basically what you want to get is a schedule. The schedule is just a sequence of statements. So every invoke will have a schedule attached, and you can simply get this by calling invoke.schedule, which gives you the schedule. We have seen in Sergi's and Eva's previous presentations that you can actually view the schedule. So for example, you will see here they got invoke schedule. Now I had to remove a lot of the parameters here. This invoke schedule in this case has one loop over a certain field space, which has several literal. Those are the loop boundaries, and then it has another schedule. Remember, schedule is a list of statements. In this case, it contains a kernel call. So how do you actually use a transformation? Now saying it's an instance of a class. So you need to do 3 things. You need to instantiate the class. You need to import it first. Then you need to create an instance of it, and then you have to use it. Now the general import statement at this stage is from PSyclone PsyR transformation import, and then the name of the transformations. Now we are currently in a heavy refactoring phase. There will be a much easier way, because at this stage you need to know where the transformation is coming from. Sometimes we have domain-specific transformations which actually come from a different path at this stage. So unfortunately, we are in between stage. For the hands-on session, I've listed the explicit name and the path where to find all those transformations you want to use. So once you've got have imported the transformation, we can then create an instance. So some transformation is an instance of some transformations. And then finally, you can apply the transformation to a single node, a list of nodes, or a schedule. And as you have seen before, this happens by calling the apply function. So you call your application, the instance that you have created up here, and then you apply, and then you give it a list of nodes or schedule that you want this transformation to be applied to. Now, some of the transformations need options. For example, if you want to collapse loops, you need to specify how many loop levels you want to collapse. If you have an OpenMP reduction, there's a specific parameter that allows you to make sure the reduction is reproducible independent of the number of processes. That needs to be specified. A very essential part of all our transformation is actually the validation check, because we need to make sure we don't create invalid code. Now, in many cases, the PSyclone will make a good guess of what's happening, but it will always be careful. In worst case, say, okay, it's not allowed, even though I as a programmer know it is safe. An example is there might be a write statement in a loop, and I know this write statement only happens if the loop aborts because something is wrong somewhere. Now, PSyclone will at this stage say, you can't parallelize this loop. There's a write statement there. But I, as a computational scientist who optimize the loops, can say, okay, yes, it is in case that an error occurs, that happens, but it doesn't matter, the loop should be parallelized. So I need to have an option to override the validation process and say, okay, please allow this to go through. That's just some of the examples of the options that we might need to provide for certain transformations. Now, both validate and apply take one optional parameter, which is called options. Now, option is just a generic Python dictionary, and it specifies those transformation-specific parameters. So it's just basically key value, and you can have an arbitrary number of those parameters. For example, we can say options equals no type check is false. Then we call the applied transformations. Here my list of nodes, and then the option dictionary. And this will actually disable any validation test that PSyclone does internally to see if all the node types, for example, the write statements, can be parallelized. A bit of a warning at this stage, if you should have a typo in the key name, like this one here. So for example, if you would write node with double D, there is no warning. Our intention is that those transformations will become more complex and you will have layers of transformation. And at the top layer, you might need to pass a transformation option down 3 levels to another transformation. So it's actually quite hard to check if all the keys are valid. We're working on a better concept, but at this stage, if an option appears to have no impact, check if you might have a typo somewhere. Now, putting it all together, this is what a very simple transformation actually looks like. So again, the transformation script has a trans function, which takes a Psy object. We then import from the library the extract transformation as example. I go into more details about this transformation later. I create the instance. I get the invoke that I want to work on, invoke with the name. Remember, invoke underscore is being added by PSyclone. The name is what you have specified. You take the schedule that you want to modify. This is basically debug output. You want to see what the schedule looks like before. Then you find the options. Now, in this case, it's empty and you might leave it out. I just put it here for your convenience in some of the exercises later. Then you apply the extract transformation to the schedule and look at the schedule again. At the end, you return the Psy object to PSyclone, which will then create the code for you. Now, what does the schedule look like in this case? So originally, it's the same one before. We had invoke schedule here, which has a loop, and then we have a kernel in here that we call. Now, after we apply the extract transformation, we still have the invoke schedule, but now here we have an extract node, and that extract node has then the loop and a coded kernel in it. So summary, we have defined what is a transformation script. They're doing very similar things. They modify them, modify the PSyR, but they're used in different contexts. One is basically invoked via the -s option as a transformation script. And the transformation script will typically have one or many transformations internally that it uses to do its actual work. We showed how the transformation script can use the transformation and to apply them. And we have looked at some common PSyclone functions to give access to the various parts of a PSyR. Now, there will be a lot more about transformations in my second half of the presentation and in Rupert's work later on as well. But since it's a very essential point, I thought I'd give it a quick break and see if there are any questions at this stage before I go into the details where we'll actually use some of the applications, transformations in detail. I don't know, Rupert, can you check if there are any questions?
Yeah, I'm looking, there's nothing there at the moment. Just for people's information, it's on Google, the Google Docs link. So if anyone does have questions, if you have questions later on, don't worry. You can just put them there, and we'll try and answer them as we go along. So no,
I'd still be around for quite some time, so feel free to ask anything later. Okay, then I go straight into the PSyData API. So what is the PSyData API? The PSyData API is an interface for an object-oriented Fortran library. On top of the library, there's a set of transformation, and that set of transformations inserts call to this library into PSyclone application. So basically, we insert code to go out of the application to call a third-party library to do something. Now, this Fortran library, the PSyData library, can either be a standalone application in some cases, or it can use another third-party library. So it's kind of interface to another library. Now, that sounds all very abstract. So let's go into some examples that we can actually use, and it might make it a lot more understandable what this PSyData API is about. So some example applications. Number one, profiling. The PSyData transformations to specify a profiling region. So you say, okay, I want to measure the region from here till the end to this area, and you basically take the corresponding PsyR nodes and give it to the transformation. Say, okay, please wrap this in a profiling section. Now, typically, the Psy API library will then call the third-party profiling library that you prefer. That can be Dr. Hook from ECMWF and UKMet offices using this a lot. It can be NVIDIA timer library. There's a DL timer. I have more libraries in progress for people who use Tau and other tools. They can all be interfaced. So just to make it very clear, the profiling transformation that we apply is the same. We just link in with a different profiling library at the end. We also have one simple standalone timer library that doesn't depend on anything, but it is very simple. I need to justify a little bit because whoever has used profiling libraries before, most of the tool already automatically instrument functions anyway. So what is the advantage that we get out of here? Now, as I mentioned before, some of the kernel subroutines are actually only working on a single element. In the Geocean API and potentially in the Nemo API, the actual kernel call is a single element. If we would leave it to the profiling library to instrument that, we would get a huge overhead, while typically the important work is actually outside when the loop is parallelized, optimized, vectorized. So we actually do not want this function to be instrumented. We want to have the whole region optimized. And most of the profiling libraries provide functions to instrument this region, but this way you're actually using existing tool chain that you already have all integrated. Plus, with this API, you actually have much easier access to the regions that you're interested in. Typically, an invoke combines several kernel schedules that have a related functionality. For example, one invoke might call 7 initializations functions. You might not be interested how much each of those functions is, but you can say, okay, instrument this whole invoke for me and just give me how much initialization time I have. The second application is to verify kernel parameters. So this means, for example, we can make sure that no input parameter to the kernel is not a number or like infinity. We can also flag automatically if the result of a kernel call contains not a number or an infinite result at the end. Internally, we have a dependency analysis running that determines what are the input parameters, what are the output parameters. So there's no need for you to specify this. It will be done for you automatically. A future request that I'll be working on in the near future is actually to verify that variables are within a certain range. For example, you might know temperature must be between a certain range of values, and we can automatically add check for that, and it will trigger saying, okay, temperature is too high or too low, and whatever. And it will be up to the application to specify those values then. The second related application would be to verify that read-only parameters are not changed. Now, initially, that sounds a bit ridiculous because obviously the compiler will make sure that I don't override a read-only parameter, a parameter that's declared as intent in. Now, that's true, but what the compiler cannot catch is you have an out-of-memory access to an array, which happens to accidentally override a read-only array somewhere. Now, yes, there's array bounds checking, but we all know this is extremely slow and not something you want to run regularly. This is an application or transformation you can apply to all your codes. It's reasonably cheap. It just computes a checksum for the field before the kernel call, computes a checksum again at the end of the kernel call, and flags if there is any difference in those two values. The third application, it's called kernel parameter extraction, or Psyche. So the idea is, before we call a kernel, we write all the input parameters to that kernel to a file. Then we call the kernel. Then we write all the output parameters to the file. Once we have this, we can create a driver that reads the file, gets the input parameter, calls the kernel, and at the end compares the results. Now I write maybe then compare the results because this isn't done yet. Now, what can we use this for? It's useful on one case, for example, for domain scientists to tuning the science. You can't just run that particular kernel over and over again and change your code and see which parameters, which formula, whatever gives you the expected results. We can use this for performance tuning. I don't want to run a whole application if I want to optimize a kernel. This way I can just run this one particular kernel, just a few hundred lines of code instead of several thousand lines, and have to wait for half an hour. It's also useful for creating unit tests. Unit tests is more and more important in the software development, even in the weather codes. And this allows you to create unit tests. Now, ideally, you have unit tests before you do the science, but this is sometimes quite hard with those large codes as we are working with. This allows you to take a kernel, create test case. And it also means if you modify the kernel, you have a consistent test case that you can keep on using and make sure you still get the expected results. Additional planned applications is in-situ visualization. So in-situ visualization means I visualize a field while the application is running. So as a domain scientist, I can pick a field saying, show me this field, and you get the graph on the screen, and whenever it changes, you can actually see what's happening. And that means you can pick up errors a lot earlier. You don't have to wait for the whole application to finish before you can visualize it. You can actually see it's happening. Another request that I was recently made aware of is to compute some diagnostics, for example, the CFL number to indicate if you have problems with the convergence of a solver. And again, this could be applied and it could be automatically monitored this way. Now, I need to be a bit careful about what this the PSyData API is used for. So it's mostly intended for use to help the natural scientists or computational scientists to do the work. It's not a replacement for example, a proper I/O library. Don't use that library to write files out. Yes, we can write files to netcdf, but it's not optimized. It wouldn't have the metadata you need in there. So please don't use it as a replacement for the I/O library. So anything that is really part of your library or your application should not be implemented in PSyData. It should be properly implemented and part of your code base. But for any tools, anything that helps you during the development process, this is the way to go. Now, I have thrown in one slide here that actually shows the code that's being automatically added. It's not actually required to understand all of this or follow all of this if you're not interested in the details. The PSyData API is quite generic, anyone can use it, but I still thought it's quite useful to give you an idea on the information we are providing and PSyclone has, so that you have an idea what other tools could be implemented with this. And that means you can actually develop your own tools, or you can suggest to us, or what about the following tools that would be quite useful. Now, the full API is described in the PSyclone's developer's guide. I'll just give a rough overview here. So if you look at an application that has the PSyData API applied, at the beginning, we create a new type, PSyData variable called, and it's saved. So we have a persistent object where we can store information. The first call that's being inserted by any PSyData transformation is a call to pre-start, and it gets the name of the module and a certain region name. Typically, you can specify to have a user-friendly name. Otherwise, PSyclone will create a unique name for you. Then there's a sequence of declare calls, declare variable. You give the name of the variable and then the variable itself, A, B, and whatever. Now that can be a single variable, it can be hundreds of variables, can be scalars, integers, fields, multidimensional arrays, anything. The declare section is then stopped by a pre-end declaration call. And then we have another sequence of calls where we provide the variables. Now, those are all the variables being provided before the kernel is called. This is then ended by a pre-end call. So this is basically the preamble that happens before we call the kernel. Then here we call the kernel or the code region that we have instrumented. And then we have a similar area here again where we start post-start. So we're now basically in the area in the sequence after the kernel call. We again provide variables and call post end. Now, People who are familiar with netcdf might see a certain relation here. netcdf, you typically have to declare all variables first before you can actually write them to a file. And this was heavily influenced by this decision. So any variable that's being provided later still is declared here. So that actually allows us for netcdf tools to declare all variables, get the netcdf metadata in, and then write the data. Some of the functions are actually optional. So if you don't have any variables for a transformation, so for example, initialization function might not have any input parameters, then there will not be no declare call or no provide function call. Profiling is actually a special case, since profiling is performance sensitive. The profiling transformation will only insert the pre-start call and a post-end call, nothing else, because for profiling you don't need variables and we don't need any of the other functions. Now many, and at this stage actually all transformation will automatically select the variables. Internally in PSyclone, we're using a variable usage analysis that tells us which variables are input parameter, which ones are output parameter. So there's no need to supply them. But they might also take a list of parameters. If you think of visualization, you might need to tell the application at compile time, okay, please visualize this field. So let's go back to the example script. And this is actually totally identical to the one we had before. But since it's a good template for what a transformation script looks like, I run through it again. The only thing that has changed, by now you know what the extract transformation is. The extract transformation is responsible for creating the PSyData code that ends its call to a library that writes the data out to a file. And again, we get the invoke we want to instrument, we get the schedule, we look before, we call the kernel, we apply the transformation, in this case no options. For debugging purpose, you might want to have a look again and then return the Psy object to PSyclone. Now in general, the PSyData libraries, they use a Fortran generic interface. You have seen there's no specification if a variable is an integer or 4-dimensional double precision field. So you have a generic interface, and the Fortran compiler is responsible for calling the right interface. Now we're using the template language Jinja to significantly reduce code duplication. So for example, for the kernel extraction, we actually have only one template for this function that writes a field to a netcdf file, but it handles 1, 2, 3, 4 n-dimensional arrays of integer scalars and doubles. So via the Jinja, we create on around 20 different functions just from one template. Now the PSyData libraries, they must be combined and it must be accessible when you compile the applications. We create an object based on this, so we need to read the mod file to know what the object looks like. We must also link it with the application and before any infrastructure libraries. Now I mentioned before, some of the PSyData libraries have a third-party dependencies. So in details, the not the number testing and the read-only testing, they have no dependencies. Those are standalone libraries and you can just link them in. Kernel extractions depends on netcdf, so you need to link in with netcdf. In many cases, especially Alfred, that's not a problem because you're already linking with netcdf anyway. Profiling, depending on which PSyData profiling wrapper library you link in, you obviously need a corresponding profiling tool. So if it's NVIDIA, Dr. Hood, or Dale Timer, you don't need to recompile or recreate your code. You just need to relink it if you want to change. So for example, if NVIDIA tool doesn't give you what you want, you say, okay, the other one's better. You can just relink your application with another wrapper library and create and use this different tool. In all cases, the safe link order is you link everything from the application, then the PSyData interface, then the third-party tool if required, and an infrastructure library. There are various classes for PSyData applications. They're defined in a config file, and at the beginning or at this stage are profile, extract, read only, verify, and not a number test. Now you can apply transformation from more than one class at the same time. So there's no problem saying, okay, I want to verify that none of my read only arrays get modified and I want to test everything for none. But you cannot apply the same transformations on the same class. So if you have profiling, you can't easily link the profiling library once with, say, Dr. Hook and NVIDIA at the same time. Now, here the location for the various PSyData transformation that we will be using later. The location is also mentioned in the README later, but I thought it's a nice overview. So the profiling transformation is called profile trans. The not a number transformation is called non-test trans. Read-only is read-only verified trans. And kernel extraction is called extract trans. There's a certain caveat in case that you are installing PSyclone yourself. At this stage, we're not installing the PSyData libraries. We're still working on the concept, okay, PSyclone is by nature script only. How do we provide libraries? So we're working a bit on this because the libraries typically need to be compiled with whatever compiler you want to use, be it the Cray compiler, Intel compiler, G-Fortran. We also will be designing a better way of creating transformations. At this stage, there is this list of where to find them. This will soon be a lot better. And some of the transformations are work in progress. One thing I want to point out here for the Alfred library, we actually do not create the driver yet. The driver is responsible for the dry extraction library. The driver is responsible for reading the written netcdf file, calling the kernel, and then comparing the results. That's outstanding work. There's actually one additional bug. If someone finds it, please let me know. I would offer a cookie, but it's a bit far away from me. So summary, I've explained what the PSyData API is. It's a Fortran object-oriented library that allows you to write tools to work with any PSyclone application, plus a set of transformation that automatically inserts the call to the PSyclone PSyData API into the call. And we have seen how to use the current PSyData tools. So before we go to the hands-on sections, are there any questions at this stage?
So again, Jörg, there's nothing written down in the Google Docs.
Okay. So if you have any questions, feel free to still ask on the Google Docs or on Slack. Now the hands-on, I'm using, and a lot of credit needs to go to Eva here, Eva's LFREC example from yesterday. Now I heard that she didn't have enough time to actually run through the third example. Now luckily that's not too much of a problem. As I said, I'm a computational scientist. I'm not that deep into the math and the science of it, but as long as I can type make, it compiles. That's all I need, and you should be in exactly this stage. So basically, all the application, kudos to Eva for doing it. It's all her work. There are a lot of templates there. We start with a simple kernel extraction of one kernel. Then we do a kernel extraction of all kernels, which are 2 in this case. And then depending on time, we can do not a number checking and or read-only testing. Now I actually modified Eva's example. There's code in there, very bad code. Don't look at it too closely. But code that would actually create nans or code that would override a read-only field. But it needs to be commented out. Now, if you look to the directory given at the bottom, tutorial practicals, LFREC building for PSyData, there's a README file in there, and that should run you through these examples. So start at the beginning. There are a lot of template files given to you for the make files and the transformation scripts. You can just use them to modify them, and it should all be in the README. You can also look back at the presentation here. Now I leave that slide on here for now, so they can check the path, and I will move around and switch to the Slack channel and be available for any questions. But if you have anything else, feel free to also just ask here.